Okay, I think I'm going to continue with the lecture, and well, this time I will be talking about the two types of vibrational spectroscopy, and I will be talking first about the infrared spectroscopy and then Raman spectroscopy. This is going to be a rather superficial introduction on infrared spectroscopy and Raman. Basically, this is the excitation of molecules with infrared energy, and then what we study is how bonds uh, are are moving around the atoms that they are connected to. So, for instance, in this slide, I show you the stretching and bending vibrational modes for a methylene group or CH2 group. And then, so we have these modes like stretching and bending. So stretching, you can see here in CH2, this would be the carbon atom and hydrogen. So the stretching is symmetrical, and you can see this vibration at 2,925 centimeters to the minus 1, and a signal in this region is shown, and then you can see also this the symmetrical stretching at 2850 and so on. So you can see scissoring or bending in plane at 1465. So what gives you this technique is the ability to identify chemical functional groups in your material. So, and the different groups or bonds can be seen in different absorption regions in the infrared spectrum. And for instance, CC bonds and CO bonds and CN bonds, you can see them at 800 to 1300 region. And then the double bond, it's around 1600. CO bond, it's around 1750, and so on. So depending upon the type of bond, you will see them in certain regions, like triple bonds is between 2000 and 2300 centimeters to the minus 1. Then we can see here two examples of how this infrared spectroscopy can be used. And basically we have two spectra, and in the y-axis you see the absorbance, and it's going down, and then you see the frequency or the wavelength, basically in centimeters to the minus 1. And the top is in the micrometer, so but they correspond to each other. So in this absorption spectroscopy is more common to see the frequency in centimeters to the minus 1. And these two spectra show polyethylene, but one of them is linear and the other is branch. And the linear polyethylene, well, in general, you can see that the main bands are shown in both spectra. As you see, 2950 or 2925, 2925 centimeters to the minus 1. You can see the CH stretch, and then at 2850 or something, you can see them, both signals. Here is cut, but this is showing the CH stretch, asymmetric and symmetric stretch. And then you see different um, overtones and combinations of different signals. But basically, you see here a double bond at 1650 or something like that, CC double bond, and so on. So the point in this is that you can distinguish between linear polyethylene and branch polyethylene. The linear polyethylene, you have a more defined spectrum. You see here slightly smaller signals as compared to this one. But in general, the linear polyethylene has stronger signals, especially at this point, around 900 and so on. So the technique is quite useful, and you can identify different materials. For instance, here you see the polystyrene. So around here you see these bands, these signals that you can identify the aromaticity. And then at here you see the CH2, CH, the CH2 stretching, asymmetric and symmetric stretching, and then the CH, the tertiary carbon here. So in general, infrared spectroscopy helps you to identify what functional groups you have and then how you can combine with different techniques to identify the chemical structure. And this technique is bulk. So a good way to deal with this is using attenuated total reflectance. And basically, what this is doing is that you have a sample, you place it in contact with the ATR crystal that usually is made of, or nowadays is made of diamond crystals. Before they were made of arsenide and some poisonous materials, but now it's pretty common to have them in diamond. Um, what happens is that the infrared is going through the crystal, which is transparent to this energy, and then it touches the sample, and it touches only the surface of the sample between around zero 0.5 and 2 micrometers. It's the depth of the analysis, and then the exact value is determined by the wavelength of light, the angle of incidence, and the indices of refraction of the ATR crystal and the medium beam probe. So the beam passes many times through this crystal and then goes to the detector. And this is a surface sensitive technique. If you can more or less use some tricks to really extract the information on the surface. Basically, what you can do is that you have, for instance, a treated material and untreated material, and then you subtract the spectrum, and then you might see the difference on the surface. Okay, now I'll be talking about the Raman Raman spectroscopy, and basically this was given to Professor Raman, is Chandrasekhara Venkata Raman, and actually he won the Nobel Prize for his work on scattering of light and the effect of this. The Raman effect is a light scattering effect, and it's also vibrational spectroscopy. I'm not going to go into details. I just want to show the technique. And for instance, you see here two spectrum. One is diamond. Diamond gives you only a single signal, very well defined, and it's quite nice to have this kind of information. For instance, if you have instead polystyrene, you have different atoms and functional groups. And you can see here that high frequency carbon hydrogen appears about 3000. So this is the CH, this is the tertiary carbon. So it appears at about 300 because light atoms with strong bonds have high Raman sheets. And so this is demonstrated here. And the opposite, heavy atoms and weak bonds have a low Raman sheets. And for instance, this aromatic structure shows very nicely at 1600. The low frequency carbon to carbon vibrations are around 800 centimeters to minus 1. So this technique is also quite useful. If you have a particle of polyethylene, you can see with Raman what kind of functional groups here you have, and then so around 3000 is the CH, around 1000 is the the carbon-carbon bond, and the CH and CH2. For graphene, you can see the two um, signals for graphene in 2D and G. So with this, I will finish this lecture, and I thank you for your attention. Thank you very much.